proofs. Okay. And first I want to impress on you that it is perfectly human, it is perfectly natural to seek proof. Okay, so if I came to your house and I said, you should evacuate, you're going to look at this shady dude and say, this guy is asking me to evacuate, okay, only because once I've evacuated, this guy's going to burglarize my house. Okay, because look at me, I'm a shady dude. Okay. So you're not just going to take my word for it that you should evacuate. For example, I claim there's a hurricane. So you're going to verify, you're going to call up the police or someone and say, do I have to evacuate? Or you might check with your neighbors. And you are seeking proof. It's perfectly natural to seek proof. Okay. So claim. The sun will rise every morning in the future. Okay, so you should look at me and say, what? Are you sure? Okay, and I'm going to say, yes, and here's my proof. So you're coming to me and I'm making this wild claim, and then you say to me, no, I'm not just going to take your word for it, you need to prove it to me. So here's my proof. Okay. For the last, 20,000 years of recorded history, years of, let's say, recorded history, and recorded history is not even that long. Okay. For the last 20,000 years of recorded history, the sun has risen every, and when I say every, I mean every. There's not been a single morning where it didn't rise. Has risen every morning. And so that's the end of my proof. Okay, are you convinced? You say, that's pretty compelling evidence. Okay, so you've convinced me. And whenever you convince someone of something, we say you've proved it to them. You've given them sufficient evidence that they have become convinced. That's a proof. Okay. Now, this is a very special kind of proof. Okay. It's a proof that is based on history, on data. Okay. And so we call this kind of proof inductive proof. Okay, and it's usually the kind of proof we use in everyday life. Okay, for us earthy beings, that's fine. That's perfectly fine. But if you think about this a little bit, you might say, well, but is that really sufficient is that really sufficient evidence to convince me? I mean, how do we know that 4 billion years from now, okay, the sun isn't going to go supernova and then not rise the next day? Okay, because every morning is a very strong statement. And if you're going to make such a strong statement, you better give me some very strong proof. Okay. So let me show you, let me highlight in a much more emphatic way the problem with inductive proof. I can use this same kind of proof to make the claim. Malik will wake up every morning from his bed in the future. Okay. Malik. Okay. Not someone else. Okay, but Malik. Okay. And then you say, what? Malik will do that? And I say, yes, I'm going to use the same kind of proof. Look, for the last 45 years, every single morning Malik woke up and, brushed his teeth or whatever. Okay. And so there's my proof. So based on all the data I have about Malik, that statement would have been true. And now you certainly don't believe it, right? And that is the problem with inductive proof. Okay. Inductive proof always leaves open the door for doubt. Okay, it's not 100% ironclad, and that is the problem with inductive proof. Okay, now we are going to be trying to set up, computer programs, and we need to prove that they work without any shadow of doubt. Prove that they work. You cannot have this, will the sun go supernova kind of doubt. Okay, so let me show you another kind of proof. And I'm going to show you another kind of proof with a different claim, because there's no way I can, so I cannot prove that the sun will rise every morning in the future. In fact, physicists don't even believe it. At some point, perhaps the sun will go supernova. Okay, but here's another claim. Okay, now I'm going to remind you of that dating game where, in every round you had 4 people sitting at the table. So, for example, you had A, B, C, D, and then you had your 4 tables, okay, and so on. And in every round, 4 people sat at a table, and then there were 4 rounds. So, in 4 rounds of the speed dating, the group speed dating club. So any person, for example, A cannot meet more than 12 people. In particular, we asked back then, is it possible to schedule the round so that A can meet all the other 15 people? The answer is now no. Okay. Now I'm going to prove it to you. Similar to here, you must look at me and say, what? And you should be blinking your eyes and raising your eyebrows and doing all kinds of things, maybe do both at the same time. And you say, I don't believe you. Okay. And that's why we need proofs, because people don't just believe what you say. Okay. So here's the proof. Okay. So observe that, for example, in the first round, A meets B, C, and D. So A meets B, C, and D. Okay. In particular, A meets 3 people. So in any round, A meets 3 people. Okay. Period. Okay. Now, in the best case scenario of a round, those 3 people have not been met by A before. But in the worst case scenario, A could have met, in the next round, if we put A next to B, C, and D. Yes, A meets 3 people, but they're not new people as far as A is concerned. They're the same people that A met before. Okay, so in the worst case scenario, A could meet 0 new people. In the best case scenario, A could meet 3 new people. So what that means is that in any round, A meets at most 3 new people. Okay. So in 4 rounds, A meets at most 4 times 3 equals 12 new people. And end of proof. Okay. And what's interesting here is that based on your own logical intuition, these statements are kind of self-evident. Okay, they are 100% true. So A meets at most 3 new people. Well, we assume that A doesn't do any hanky-panky and cheat. Like in the middle of the round, A jumps from this table and moves to another table. Okay, thereby meeting more than 3 new people. No. Providing that everyone follows the rules. Okay, this argument has no room for doubt. Okay, we have no doubts now that, A cannot meet more than 12 people. Okay, ironclad, you can take it to the bank. Okay, and this kind of proof, which is not based on data, but which is based on reasoning and deduction, this kind of proof is called deductive proof. That is the kind of proof that we are interested in when we talk about a proof in mathematics. Okay, we're not interested in, all the numbers that I have seen so far satisfy this property, okay, and therefore I'm going to claim that all numbers satisfy this property. That's a proof that's based on data. That's called an inductive proof. Now, certainly, inductive arguments can give you guesses, can suggest patterns, and that's the whole point of tinkering, but they don't formulate a proof based on inductive arguments. Okay, deductive proof. So let me show you some examples of deductive proof. Proofs that leave you with no doubts. Okay, so let's talk about square numbers and when are they even. When are squares even? Okay, and when you look at this problem, it looks very hard. Okay, and we have no idea what the hell are we even talking about. Okay, so we're talking about numbers that are squared. Okay, and since we don't know even anywhere to go at this point, the first step is to play around. Okay, that means the first step whenever you're attacking any problem is to tinker. Okay, so tinker. Okay, so let's look at numbers and their squares. So n squared. So n can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the squares. Okay, squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Okay. So when are squares even? So let's look at the even squares. So I'll box it for you. Even squares. And that's the beauty of tinkering. So hopefully when I was boxing these even squares, you should observe a pattern. That look, corresponding to the even squares are the numbers they came from. And it's never the case that an even square came from an odd number. All even squares come from even numbers. And also, if you look at the odd numbers, okay, and the even numbers, all the even numbers have even squares. Okay, so now that's the benefit of tinkering. Now we have gotten some understanding of this problem, and okay, we're ready to make some guesses. So, guesses. Okay, and sometimes we call such guesses conjectures. Okay, so my guess number 1. Okay, any even number has an even square. Okay, every even number has an even square, and conversely, you know, if you ever encounter an even square, so any even square, it came from an even number. Okay, now I'd like to just, you know, emphasize that these are two different statements. This makes a statement about even numbers, okay, and what are their squares, and this makes a statement about even squares and where they came from. And now you should be looking at me with your squints and this and that and saying, really? Okay, so I'm going to prove it to you because you asked. You said, I don't believe you. Okay, so how could we prove this? Well, let's start with claim number 1. Okay. Any even number has an even square. So if you remember to when we defined the set of even numbers, we said that any even number, you know, E, okay, is of the form 2k. It's twice some natural number. Well, it's twice some integer. Okay, if we wanted to define all even numbers. Okay, so it's twice some integer. Okay, so this is a generic representation for an even number. Okay, well then let's look at the square. E squared is equal to 4k squared, which is equal to twice 2k squared, which is twice some other number, so this is even. Okay, so if you started with an even number and you squared it, we just proved that the result has to be even. Okay, so that's the proof. No doubts. There's no way around it. If it's even to start with, its square is even. So that's proved. No doubts. This is an example of a mathematical proof. Now, in sort of proving this, I'm using all kinds of things. You know, I'm digging into your chest of background corresponding to everything you learned in high school and algebra and so on, that, you know, an even number is twice some other number, And when you square, you can square each of these terms, so you get 4k squared, and these are all things that you have learned. I'm using stuff that you already know. The second claim, that any even square came from an even number, which we got by observation. So that's by induction we got this, and now we need to prove it by the inductive approach, by the data-driven approach, by the tinkering approach. We got the claim, now we have to prove it. Okay, this is a little bit harder. Okay. So let us consider the claim that any even square came from an even number. Okay. So n squared, let's say n squared, so the number squared, so that's what it means for the when you're considering a square to be even. What we're saying is that n squared is even. Okay, that's what we're saying. Okay. And now I want to convince you that n has to be even. I want to convince you that n has to be even. Okay? I have to convince you, because you're squinting and raising your eyebrows and all kinds of things. Okay? And so, how do I convince you of this? Well, if it's, let's consider, well, if it's not even, well, if it's not even, then it's odd. Okay, so what does it mean if n is odd? So if n is odd, it's of the form 2k plus 1. Okay, so it's twice some integer plus 1. Okay, so if it's twice some integer plus 1, well then let's have a look and see. N squared is equal to 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is twice 2k squared plus 2k plus 1. So it's twice something plus 1, which is odd. Okay. So if n is odd, the square has to be odd. That's similar to the claim that if n is even, its square has to be even. If n is odd, its square has to be odd. And since we have a square that's even, it means that n cannot be odd. Well, if n cannot be odd, then n has to be even. So n cannot be odd. So the only other case that's available for us is n is even. So n is even. And that's the proof. No room for doubt. Okay. So, interesting. Whenever you have an even number, its square is even. Whenever you have a square that's even, you know that the number it came from is even. So if someone comes to you and says, I got this number 144. I know that it's a square. Can you tell me anything about the number it came from? Well, in this particular case, we can compute the number it came from. Okay, we can compute that, the number. We can compute the number it came from. But even if we couldn't, we can say for sure, because it's even. We can say for sure that it came from an even number. It's the square of an even number, and sure enough, it's 12 squared, and 12 is even. Okay. So that's an example of a baby proof. Okay, about when squares are even. Let's go to a much more complicated scenario. Extremist parties.